In this module, we discuss what determines the direction of a spontaneous change in a system's state. The first law of thermodynamics constrains the range of possible processes to those that conserve energy. It prohibits, for example, machines that can work indefinitely without an energy input. However, not all processes that satisfy the first law of thermodynamics actually take place. We have previously discussed the concept of a reversible process. It is a process that can be reversed even by the slightest reversal of the external driving force. Specifically in the context of thermodynamics, a process is reversible if during the process the system always remains in equilibrium with its surroundings. As spontaneous processes, we understand processes that run without any external influence. The term spontaneous doesn't imply that the process occurs immediately, but rather indicates that it is highly likely to occur if all barriers to the change are overcome. There is also a concept of irreversible processes. Once an irreversible process has occurred, the system cannot return to its original state without external intervention or another process taking place. In thermodynamics, spontaneous and irreversible processes are basically the same. For the sake of completeness, let us also introduce non-spontaneous processes. A non-spontaneous process, while satisfying the principle of the conservation of energy, will not occur on its own under given conditions without external intervention or the occurrence of another process. Given the variety of potential outcomes for a system's future, certain questions naturally arise. How do we determine if a system, given a certain state, is in equilibrium and won't undergo spontaneous changes? If a system isn't in equilibrium, which direction will it spontaneously change towards? That is the core of this module. It is essential to clarify that it is not a tendency towards lower energy that defines the state of equilibrium and the direction of a spontaneous change. The first law states that the universe's total energy remains unchanged in any process. In many instances, our everyday experience can guide our understanding of whether a system will undergo a spontaneous change, and if so, in which direction. But for complex scenarios, we can't just rely on intuition. Imagine dropping an incompressible ball from a certain height. It meets a solid floor and is halted abruptly. For simplicity, let's assume there are no rebounds. The question arises, where does the ball's initial mechanical energy, both potential and kinetic, end up upon impact? It doesn't disappear. Instead, the energy from its ordered, directed mechanical motion disperses into the disordered, random thermal motions of molecules around the impact point. Experience teaches us that this is a spontaneous process. Now, picture a stationary ball on a solid floor. Energy from the random thermal motion of the floor's molecules concentrates at the ball's resting point and gives the ball a mighty kick up. The ball gains an ordered, directed mechanical motion, and the floor experiences a slight temperature reduction. For this to occur, energy from the myriad vibrations of the floor's molecules must localize to fewer atoms around the contact point. Moreover, while thermal motions are random, a prevailing majority of the floor's molecules would need to move synchronously in one direction to propel the ball upwards. The likelihood of organizing such disordered thermal motions into a single directed motion is so low that it is basically non-existent. Consequently, this makes the second process the opposite of a spontaneous process, a non-spontaneous process. The examples we have discussed illustrate how we can determine the direction in which a process spontaneously proceeds. This determination isn't about the energy balance, but rather the distribution of energy. Generally speaking, spontaneous processes results in the dispersion of energy. In a spontaneous process, the energy transforms from a more ordered form to a less ordered one. It's also important to note that matter exhibits a similar tendency to disperse. A gas won't spontaneously contract. To achieve contraction, the random motion of its molecules would need to synchronize, causing them all to move into the same region of the container. In contrast, expansion into a larger volume occurs spontaneously, as the random motions of the molecules naturally spread them out, filling the entire container.